And Ricardo said, astrophysics is really boring.
So exoplanets, what do you mean? Come on.
So you should tell us about these sorts of things. And so after coffee, I sat down and I wrote down the sort of briefest possible introduction, I think, that you can give into this topic, which is large-scale structure perturbation theory, which is something that I've worked on in one way or another. I'm more of a practitioner than a developer, but I've wielded it as a tool extensively during all of my time in grad school. I remember when I was an undergrad, working here at ICTP, asking Rafael Porto, Rafael, I want to learn this. Can I please, can you teach me this? And he said, no, you have to eat your rice and beans, arroz, feijão, primeiro. And take all of the classes before you can learn this. So
now I have done it.
Not really, but I guess, on paper maybe. So it's a field where I think it changed a lot, especially starting in sort of 2010. Não tá pegando? Assim? Puta, tá. É que com o óculos estava...
É do outro lado.
É como os pais mesmo, você nunca assistiu os pais mesmo.
Ah, this makes so... Okay, this is more comfortable.
Não, deixa perto.
So, what was I saying? I forget. Oh yeah, so it's a field where I guess, as far as references, there was this, it's actually quite a nice perturbation theory review paper in 2002, as people had sort of first started calculating a lot of these nonlinear perturbative corrections to structure formation. In 2010, the story really changed. There's this paper that I mentioned by Baumann and Nicolis and Senatore and Zaldariaga, which kind of fixes a lot of the problems that I'll try to talk about in this perturbation theory. I think the most modern and the best notes are actually a class that Tobias Baudorf taught when he was at Cambridge. If you can't find these online, you can email me. I guess I should put my name right. So you can email me and I can send you the notes. I think it was sort of the first very modern set of lecture notes that were comprehensible, that were written by people. It's a very famous textbook by Donaldson and Schmidt, of course. Donaldson wrote the first edition. When they went back to write the second edition, Schmidt, Fabian said, well, we really have to update this because perturbation theory is such a standard part of what we do nowadays in cosmology. So this has some discussion. And then finally, a friend of mine, Oliver Philcox, was asked to teach about this topic at Cosmology on the Beach. And so he wrote a very nice set of lecture notes on this topic as well, and you can see his website. Okay. So let me tell you a brief overview of what the things that I want to discuss are. So first I want to set up the physics problem that we want to discuss. And feel free to interrupt and heckle me and yell at me at any time. Which is this, the post-recombination universe. So recombination, of course, is when the CME first forms, when the temperature of the universe drops below 13.6 electron volts, and that's basically when the photons don't really have enough energy to just ionize hydrogen atoms when they hit them again. And so this means that you get neutral matter forming, the photons just kind of free stream out, and then the dark matter and the baryons are just left to evolve gravitationally with nothing really interesting happening. So I guess when the universe becomes really uninteresting, that's when this topic starts, but so a few things show up. So on top of this, I'm going to build up what's called Eulerian. You also see it sometimes called standard, but I don't like that because I work on the other part of perturbation theory, which is the other frame. So we normally try to refer to it as Eulerian perturbation theory, which is, I think, it's actually not the first way that these calculations were done, because Odovich did the first really nonlinear perturbation theory calculation in '74, but this became very popular for a while.
So Eulerian, because it works at the level of equation of motion?
Yes, exactly. So I'll explain. Basically, this is a perturbation theory at the level of the equations of motion. So it's a fluid dynamics problem. So you can either write it as a fluid dynamics problem in the Eulerian frame or in the Lagrangian frame. And then the mathematical structure of the theory is actually quite different. You can show formally that order by order, loop by loop, the predictions are always the same. But there are a lot of tricks that you can do in the Lagrangian frame that simplify things.
Okay. So the 2010 basically revolution was to move to the Lagrangian framework.
Sorry, say that again?
The 2010 paper that you mentioned.
No, actually no. So the 2010 revolution was kind of, when people write this Eulerian prediction, and I'll show you, it's just, there's no expansion parameter. So it's a perturbation theory with no expansion parameter. You are integrating over loops, you're integrating over all momenta, all scales of the problem. These are really nonlinear, and so the predictions were actually just didn't make sense.
So they systematized it.
They systematized it, showed a formal sort of integrating out procedure that lets you control divergences, get some sort of renormalization structure, counter terms that show up, that sort of thing, which I'll try to get to. So then I want to talk about divergences, because so these are divergences in Eulerian perturbation theory and how they come about. Then I will basically talk about how to cure them. So this is EFT, and specifically I want to introduce this construction of this effective stress tensor, which solves a lot of the problems. So this coarse grading procedure that people do, which is how this was first set up. I think this isn't really the modern way that people think about this. It's more this Wilsonian idea of you just look at the structure of the loop integrals, you isolate the divergences, and you just put in the counter terms that make sure that the theory is finite at the end of the day. But there's this nice kind of intuitive explanation that lets you understand from a bottom-up perspective why you would expect these corrections to exist in the first place. So I'll talk about this. And then, if we have time, I kind of just want to give a brief, where do you go from here? Because this is sort of the first step in learning all of these things, and the field is quite rich, and there's a lot of different branches. And I'll just motivate some of them. But you really need, I think, quite a few lectures to sort of go over all of the facets. So let's start with this post-recombination universe. If you open a cosmology textbook and you're trying to study the very early, very dense, very hot universe, you might find something that looks like this following figure. You're studying a GR problem, you're writing down some metric. This metric is going to couple every species that is doing something interesting in the early universe. So you can write down neutrinos, and they'll decouple from the matter fluid, but they'll still have some sort of gravitational influence, and they'll also be back reacting onto the expansion of the universe because they'll be hot. You can have dark energy, which doesn't play a role in recombination, but of course at late times you really have to worry about this. You'll have something like dark matter. And then you have the components that have sort of non-trivial interactions, right? So you'll have what we call baryons, and cosmologists call electrons baryons, despite being manifestly not a baryon. This is just anything that's standard model matter, basically. Boltzmann actually specifically makes a distinction for electrons. And so you not only have metric couplings, and so these fluctuations in density are sourcing the fluctuations in the metric, which respond to everything else. In the very early universe, these are scattering. And then finally, you have photons. And of course, photons can also scatter off of electrons. You have something like Thomson scattering, which is the main process. This is Kokron.
So, but after recombination, you're not supposed to have three electrons, no?
Huh?
We're after recombination, so why you want to separate electrons and values?
Well, because right now I'm just setting the stage for the post-recombination universe. But I want to make sure, I don't know the background that everyone has, so I want to make sure everyone's on the same stage for pre-recombination. So you're trying to track all of these species simultaneously. Really what you're trying to track is something like the phase space distribution of a species alpha, so its position, its momentum, as a function of time. And this is conformal time, but you can just treat it as time. It just makes the calculations a little bit simpler. And a standard cosmology class is going to teach you how to write down the equations of motion of all of these fluids at the same time. You're going to write them as linearized equations because all of these fluctuations are very small from a perfectly homogeneous universe where nothing happens. And then you're going to plug all of these into something like class or CAM, which are the two main codes that solve for all of these things. And what this is going to give you is a prediction of the spectrum of matter fluctuations. And so this is the building block where we kind of want to start everything. And And so the basic idea from this is that you can write the density contrast of any fluctuation as the density at a point at some time minus the average density for that species at some time divided by the average density at that time. And the Fourier statistics of this thing are what these codes give you. So the fundamental building block for everything that I'm going to do, and if you don't care about any of this physics, the idea is just that you can solve for this problem, and this gives you the initial conditions for what we're going to study. So these initial conditions are that...
Linearized, of course.
Yes, linear.
And this, of course, is justifiable because the perturbations are small.
Yeah. Yeah, so all the perturbations away from a perfectly homogeneous universe are very small here. The dark matter fluctuations are on the order of 10 to the minus 3 at the time of recombination. So it's really quite perturbative if you're expanding in powers of that. But the basic building block is that this ends up being Gaussian distributed due to inflation and with a very specific form. And so if I take the Fourier transform of this and I look at a correlation function or a power spectrum between two different Fourier modes, I ran out of space. But this fundamentally at early times, and so the linear solution is that this is Gaussian, randomly distributed with a spectrum that is completely well defined. It's diagonal, so there's no correlations if k and k prime are different, if you have two different wave numbers, and you just get this one function, p linear of k. So
when you say initial, it will be any time before recombination, basically.
Even at recombination, so what this code gives you is the evolution through all of time of the recombination, even after recombination, but then it gets simpler. But for what we're going to see is that when I try to write down the theory for these fluctuations post-recombination, I will always have as a building block the linear solution, which is this power spectrum here. So this function is quite simple. So as a function of k, this might look something like this. So this is proportional to k at large scales. There's also an ns minus 1 term, but I'm neglecting that right now. There's some peak, which picks out a preferential scale in the evolution of the universe, which is the scale of matter radiation equality. There are some fluctuations here. This is what we call the baryon acoustic oscillations, which have information about the baryon density and the dark matter density. And then this is kind of just a power law. And so this goes as roughly k to the minus 3. And so this is the initial condition. This is the building block for all the calculations that we're going to do. So just keep this function in mind. Okay, so now let's talk about, any questions so far? So now what I want to do is basically set up the problem of what is the dark matter fluctuation doing. So if we know that it's this Gaussian field with very small overdensities, but more generically, what can I say about the distribution function of dark matter? And so this is just telling you what the density of states is at any given time that are at a position x with the momentum p. That's all that it is. It's a distribution function. And we know that the dark matter is not interacting with anything. It's cold. It's collisionless. And we know that it's the dominant component of the universe at the time that the CMB forms. So I'm just going to neglect all of the other components. And all that it's going to do is just evolve under the Boltzmann equation, essentially. And since it's collisionless, there won't be any collision operator. So all that I'm going to do is say that this distribution is just stationary, essentially. Of course, this isn't a very helpful equation right now. This is the Vlasov equation. And so what we want to do is massage this and try to get this into a form that will give us a little bit more intuition as to what's going on. And so the idea is that we then just expand this in terms of partial derivatives. So really, this is actually equal to something that looks like df d eta. So eta is always the time derivative, just keep that in mind. Plus dx d eta, so each of the individual components. And then a momentum derivative as well. And a derivative of the distribution function with momentum. and this is equal to 0.
Why is it constant with time? So we understand.
The whole distribution is conserved, the phase space distribution, because this particle is not being destroyed, it's not scattering, it's not being produced. So the total phase space distribution has to be conserved as a function of time. And then, of course, this is the total derivative, but then if you break this into partial derivatives, there can actually be some dynamics. So then, and this right now, this is always valid on sort of small scales, smaller than the cosmological horizon. There's a lot of subtleties if you think about scales that are larger than the horizon and smaller than the horizon. Go read Boltzmann, take Rossetti's class. I'm not going to get into that. So we're really going to be in actually a very Newtonian regime here. So let's massage this a little bit. We can sort of identify this just immediately as something related to the momentum itself. So this is just sort of a definition of the momentum of all of these fluid elements. And it's also important, so here we're treating actually something that's particle-like, so we can always assign a mass to any individual object. So if you're treating something like fuzzy dark matter, some scalar field dark matter, this actually changes a little bit, and you have to be careful with how you set up the perturbation theory.
So A is the scale factor.
A is the scale factor, yes, thank you. This is always the scale factor of the universe. And then this term over here is actually just, well, Newton's second law. And so this one we can just write as minus A gradient of the gravitational potential. And then to close the system of equations, because in principle I have the distribution function and I now have the gradient of the potential as well, I'm also going to specify that well, I'm going to do that in a second. But basically, yeah, so there's some potential, and this is going to be sourced by the Poisson equation. So the Laplacian of the potential is the density itself.
So those are physical particles
Yeah.
there.
No, this is all in Comuni, right?
D over A is
Yeah, this is in physical right now. Yeah. Yes, it does. So this is a 7-dimensional partial differential equation. It's nonlinear. So that's just not what we're going to solve. Instead, we're going to try to reduce this into a set of equations. Instead of one really complicated equation, a set of equations that are simpler and in fewer variables. And so we're going to use a trick from statistical physics, which is this so-called decomposition into the BBGKY hierarchy. So it's like Bogolyubov, Bardeen, something. And the idea is that if this is a statistical distribution of the entire dark matter fluid, instead of trying to solve for that, I can try to solve for moments. The mean, the normalization, which is the 0th moment, the variance, etc. And so what we can do instead is define moments of this distribution, which will be something like the density is what I get when I integrate over all momentum. And so this looks like this integral here. I can do the same and define a velocity, which now gives me 1 power of the momentum here. So I have a normalization, which is like 1 over just an integral over all 3 states f. And then I have an integral here, d3p. And then the velocity of every single fluid element and the distribution. So this is the first moment. I can do the same and also define the stress energy tensor at every point of this fluid, which is going to be this normalization. And then 2 powers here. So let me just write it pi pj over am squared f. And so if I have defined these moments, right, so this is density, this is the average streaming velocity at any given position. So what's the average if I weigh over every single momentum component that this can have? So this is mean streaming. And then if I also define this velocity dispersion tensor, these ingredients I can use and these moments to simplify that equation. So now we go to that complicated Vlasov equation that we wrote out in that way. keep this here for a bit. And all that I'm going to do is basically do an integral over all momenta of powers, of n powers of the equation. So this is what I mean by taking moments of the equation. And this always has to be equal to 0. Because I can always just integrate the right-hand side. That's just 0, so the integral of 0 just gives 0. And so if you play this exercise, for n equals 0, you get a constraint equation. Exactly. And so this equation, so delta is that overdensity that I just erased, so I guess I can keep this here. So you get a derivative in conformal time, which I will denote by a prime, plus the divergence of this component, 1 plus delta v. This is equal to 0. So this is called the continuity equation, and just expresses conservation of mass. So in the absence of producing or annihilating dark matter particles, all that I'm saying is that the flow of density through any given point is just given by all of my inflowing dark matter and outflowing dark matter to that point. And this is what this expresses. This is just mass conservation. If I do n equals 1, then I get a vector equation, because I'm taking a vector moment here. And so what I then get is a derivative, and I get an equation for the velocity, which is the following. And I'll define this h in a second. You get a term here which looks like Vj partial j vi. So you're coupling these indices together and summing across them. And on the right-hand side, you get a term that looks like di phi, so gradient of the potential, minus a term that looks like a divergence of that stress tensor that I had defined over there. So specifically of rho times sigma ij. If I were to do this for n equals 2, then what I would get is an equation that has the time evolution of sigma ij in terms of some 3-indexed tensor wij(k), and you can do this infinitely. And if you do this entire infinite hierarchy, that's equivalent to solving that equation. We're not going to solve the infinite equation. So what we're going to do instead is assume the following. Because I said that my dark matter fluid was pressureless and collisionless, it's this perfect fluid, I can just completely neglect this sigma ij tensor. So this is the stress energy tensor. If you, and exactly, because this is 0, so all of the other higher terms are 0. They're source, and so you turn it off. And so this is what people say is standard perturbation theory, or one of the founding assumptions of standard perturbation theory, or Eulerian perturbation theory, is basically saying that this term here is approximately equal to 0, we can neglect it.
So I've heard people that sometimes work on interacting dark matter models.
Mm-hmm.
This implies that when they interact with these kind of things, they have to compute the whole hierarchy of the models.
Not necessarily. So when people work on, for example, interacting dark matter models, if it's something like dark matter, dark energy interaction, so if you have a coupling, then what you would do is you would actually write down the hierarchy for each of these fluids individually. So you would have a dark matter fluid and you would have a dark energy fluid, and the continuity equation would have a term if you have sources or sinks that couples them. And if you have scattering, then you would have a term here, which looks like some sort of drag term. So it's going to be the difference of the velocity divergences.
Right.
Is it right that if you have massive neutrinos, it's also an integral of 0?
No, so yeah, if you have massive neutrinos, then they actually contribute to this, because this is what would look like an anisotropic stress tensor. So it's actually also off diagonal. If you just have pressure, then it's diagonal. There's a paper, a few people have tried to do perturbation theory with neutrinos, but it's really difficult. Basically because they're really fast. They have a very large thermal velocity, so they violate this cold assumption. And they basically you're perturbing on top of a very different distribution when you write this distribution function approach. I can point you to a paper by Leonardo and Matthias about this, but it's very hard.
But is there a small parameter that makes you jump from one end to the following one, like the velocity of the particle?
So right now, no, I haven't made any assumptions, but also this is, if I cut this off, this is still completely valid for an arbitrarily nonlinear dark matter fluid. So if I could put this, that is perfectly cold and collisionless. So if I could put this on the computer and solve it, I would get an exact result.
No, but I mean, for small velocity, there is an apparent, when I move from one end to the following one, I just have to pay one extra v, don't I?
Well, you have to pay, but it's also, the complexity is a lot larger. So if you think of each tensor, so the velocity is 3 components, this is going to be its symmetric, so it's 6 components.
No, but at the level of how strong the effect is an extra v, isn't it?
It's an extra v, yes. Yes, exactly. So we're not going to treat this, we're going to look at the system here. And so we're going to first make this perfect fluid assumption and set this to 0. And then we're going to make one more assumption, which is that the initial conditions of the universe are small enough that my velocity vector is actually irrotational. So there's no curl component. So if you remember ENM, when you write any sort of Helmholtz decomposition of an electric field, there's a contribution that comes from a gradient mode, contribution that comes from a curl mode. So what we're going to be assuming is this irrotational flow. And so what I'm going to be saying is that my velocity field can always be written as something that looks like some velocity divergence. So I'm just going to write it like this. And there's no contribution basically which looks like we're not done though, because again we only have an equation. We have 2 equations, but 3 variables. Because we have the dark matter density, we have the dark matter fluid velocity, but we also have this gravitational potential. So when you take a fluid mechanics class that's based on Earth, this is the easiest, most boring term. This is just G. Actually, if you go to like rotating frame, this sort of thing can actually matter. You get other contributions. If you're looking at the entire Earth, like 100 of kilometer scale ocean waves, it's kind of interesting. But here, this is actually a really important term. Because to close the system of equations, I'm also going to remind you that this fluid is self-gravitating. So where can I write this? I guess I'll just write this here. So there's also a constraint equation which comes from the Poisson equation. So the Laplacian of this potential, I guess I wrote it like this. The Laplacian of this potential is equal to 3/2 omega matter, the conformal Hubble parameter, times delta. So it's just written in a way, this is just standard Poisson equation, but in cosmological units is what we call it. One more thing also, so this H term is what we call the conformal Hubble parameter. So this is like A prime over A. So this term here is kind of also different from terrestrial fluid mechanics because this tells you what the contribution from the expansion of the universe is. So this looks like a friction term basically, at the level of the equations. Okay. This is still nonlinear though, right? This is a nonlinearity, this is a nonlinearity. This is kind of a weird non-local contribution because it's the gradient of something of this potential. So we still have to do some work before we can go to the actual large-scale structure perturbation theory. But this is the problem that we're trying to solve. So we have some initial Gaussian density fluctuations with the spectrum, and what we actually want to compute is how is the spectrum going to evolve over time. Okay, so good? So the first thing that I'm going to do is just write those same equations, but I'm going to go to Fourier space. So I'm just going to write them in terms of momentum. And because the spectrum is diagonal in all momenta, so that's just a very convenient basis for you to treat this problem, is the momentum basis. And so what you get is delta of k plus theta of k. Actually, I'm doing 2 other things as well. I want to convert this to a scalar equation, so I'm going to take the divergence of this equation over here. And I'm also going to replace this with the Poisson equation, because when I take the divergence, not only is this going to become a scalar contribution, which is just this velocity divergence that I wrote, but this also is just going to become the density again. And so this equation looks like the following.
Sorry, but delta and theta cannot have the same due date. Data is dimensionless.
Yes.
Eta doesn't seem to be, no?
You define it in units where it's dimensionless as well. Because it's a velocity, there's a C term, it's kind of...
No, V is dimensionless, but then theta cannot be. No? If V is dimensionless, I agree, but theta is not, cannot be.
You can always add in Hubble parameters to make it dimensionless, basically. H is just 1 over time, so you can always just play around and make it dimensionless.
Okay. So I throw in the Hubble parameter to adjust the image.
Yeah. Sorry, this is delta prime over here. This is...
First equation that you wrote comes from the first equation.
This is literally the continuity equation, but I wrote it in Fourier space.
No, but that is fine. No, you don't need the Hubble parameter because then theta and delta prime are the same dimension.
Yes, that's also true. Yeah.
No, theta is inverse of length, so it's okay. Now it's okay.
Yeah, sorry, this was delta prime, because
Yes.
there it works out, yeah. And then I have this.
So it is dimensional.
Yes.
It turns out that this term from the Poisson equation is actually a linear contribution. So I'm putting all of the linear terms on the left-hand side. And then all of the nonlinearities on the right-hand side. And then just to make this a little bit not as large, I'm just going to basically, if I have some integral and I do a sub like this index, it's a d3k over 2 pi cubed integral. And so this is k squared times k1, k2. There's also this momentum conserving delta function here that I just didn't write out. 2 k1 squared, k2 squared, theta of k1, theta of k2.
But then you're considering non-linearities in the other equation, but not in the Einstein equation. Is that fair? Because the Poisson equation is the Einstein equation linearized.
Yes, so yes, and the paper by Leonardo et al. Shows that the back reaction is basically really small in the potential from any density fluctuations. Because the non-linearities of the Einstein equation are only important.
Okay, because phi is small, pi is small.
Yeah, and also basically the contributions that actually matter are terms that depend. So it's like terms that are like phi prime, h phi prime would show up.
Yeah, because phi is small, delta is not, but phi is. So
Yeah. So this is the same equations, but I've now written them in sort of the way that we will treat them for the rest of this discussion. So it's an evolution equation for delta k. And actually notice that it's not symmetric in k1 and k2, right? But there's a momentum conserving delta function, and I'm coupling my velocity field to my density field in this very prescribed way, actually. So it's k1 dotted into k1 plus k2, so it's not symmetric for k1 and k2. And then my evolution equation for theta is coupled through the Poisson equation back to the density, but then all the nonlinearity comes in the velocities themselves.
yeah, but what do you mean is not symmetric? You can reshuffle. I mean, they are integration variable. You can rename them.
Well, yeah, but it's just because the structure of the nonlinearities here, the momenta are always these two fields. I mean, you could symmetrize this, but if you just write out this coupling, the mode coupling is not symmetric a priori. Because one is always concerned with, one momentum is always the theta variable, the other one is the delta variable. And so this is the fully nonlinear equation. This is still actually valid to all orders, right? And so what we're going to do is linearize it, and that's easy. We just take the right-hand side, set it to 0. So if you linearize it, so first we linearize, and then we take a time derivative of this equation over here. And what this will do is it'll let us just pick out basically this theta prime term over here. We can sum in with this theta term, we can plug it in back here, and you can just write this in terms of one equation. And the equation that you get is delta k prime prime plus h delta prime k minus 3/2 omega matter h squared delta k equals 0. So this equation is called the Mészáros equation. And so this tells you two things. One is that, unsurprisingly, when you linearize the equation, all of the k modes evolve independently. There's no coupling from a k to a different k prime. And second, that all that matters basically is the background of the universe. So h is just set by the background components. Omega matter h squared is set by the background components. So you can derive all of the time evolution of linear theory only from this approximation, or only from this equation. And this is how you get basically that matter domination gives you the largest possible growth, that dark energy domination stalls growth, etc. So the standard cosmology textbook will kind of go really into detail in solving this. But this is just a starting point. So this isn't really the point that I wanted to make. What I wanted to make is, if we have a linear equation and we have a linear solution, what can we do, right, to plug back in the linear solutions and get something that is sort of higher order? And that's where we begin. So another thing that's interesting, right, is that if at linear order, since we set this to 0, density and velocities are just exactly, are just related to each other by some sort of factor. And that means that at linear order, densities and velocities evolve in the same way. At higher orders, we're going to see that that's not the case, because then the momentum coupling structure is slightly different. So now I'm going to make a very unrigorous assumption, but that's how people treated it, which is basically I'm going to say, oh, delta is in some sense less than 1. And also now theta is in some sense less than 1. And now I'm going to try to solve for this in perturbative sense. And so the first thing that I'm going to do is I'm going to assume that we're in matter domination. In matter domination, it turns out that the time evolution is just scale-free. We just get something called an Einstein de Sitter universe. And that just makes things a little bit easier. Yeah, you can go to the references and they show you how to treat the more general case. But the basic idea is that the linear density only grows as the scale factor. So all that I'm going to assume now is search for the following solutions. I'm going to look for something that looks like delta of k and eta is going to be a sum of powers of the scale factor times something with a non-trivial momentum dependence, but that doesn't evolve in time. So I'm assuming that these solutions are always separable. And then here I'm going to do the same. And so this is just this dimensionful thing that lets you write in terms of dimensionless solutions. So a sum of ai, eta, and some theta to the I of k. Right? So all that I'm saying is, well, whatever this thing is, it's just going to be some sum of from I to infinity, from I to infinity. And it turns out in the scaling universe, everything is separable, so my time evolution is just powers at the scale factor, and the scale factor is the linear solution. So this makes some sense in which things are small, right? A equals 1 today, so in the past, A is smaller than 1. So the second order correction is going to be some smaller number than 1 squared, cubed, etc. So maybe this is some sense in which things are small, but we'll see that this actually doesn't work very well.
So A again is a scale factor.
A again is scale factor.
So power I.
Yes. So this is what's called this Einstein de Sitter ansatz, basically. And you can show that it works at all orders, basically. And the reason is because this H is A prime over A, and so you can just write it into very easy form in Einstein de Sitter, and then all of the solutions just become separable, basically. So now what I'm going to do is basically write on my left-hand side my second order solutions, and on my right-hand side, theta 1, delta 1, and theta 1, theta 1. And that'll give me my second order solution. I'm also going to call this momentum coupling term here beta of k1, k2. And this here I'm going to call alpha of k1, k2. Yes, so I think that's all that I wanted to do. I guess one other thing that might be worth pointing out, so I don't know if you know, these bootstrap approaches are really popular nowadays. So instead of doing all of this, what people have tried to do is point out that all the sources of nonlinearity are only given by combinations that look like theta, theta, beta, and theta, delta, alpha. And people try to bootstrap the solutions to large-scale structure. And then impose constraints like the equivalence principle to like kill terms that aren't allowed and see what you get out. And it's
bootstrap to higher order.
yeah, basically like they try to write something that isn't a perturbative series, but some sort of like bootstrap approach where you just enumerate at some order all possible contributions, and then you impose external constraints to try to kill off contributions which aren't physical, instead of trying to do something informed by the dynamics. Because right now I'm going to plug this back into these equations, right? But what they're saying is that all the nonlinearities are sourced by this and this, and so this kind of gives me a basis for all of the nonlinearities that I could possibly write down.
So in the Lagrangian approach, you make this, you work with the Lagrangian that gives you this equation of motions.
No, actually. So in fluid mechanics, the Lagrangian approach is
It's a frame, right?
it's a frame. So I can ask what my density is at any given point in my box, and what the aggregate velocity is of all the fluid components in this box. So that's Eulerian. Or I can treat each individual fluid particle and treat its motion over time, and that's the Lagrangian approach. So the Lagrangian approach, what you're doing is you're taking the initial conditions of the universe, you're putting down a set of test particles, and then you're tracking the evolution of every single one of these test particles over time. So then it's really just Newton's law, right? It's just every particle follows F equals ma, basically, where the potential is sourced by every other particle. Okay.
So I starts from 0?
I starts from 1 because the 0th order solution is that the mean is 0.
So I starts from
Yeah.
and I equals 1 is the solution of the homogeneous equation.
I equals 1 is a solution of the linear equation. So if I set this term to 0 and this term to 0. But that's just what we get when we solve the Mészáros equation, basically. And the K-mode structure is set by the power spectrum that I wrote originally.
Right. So in that case, for I equals 1, delta tilde 1 is 1. Is that
For
right? Because
no, delta tilde 1 is just delta. Is just the delta from the primordial curvature fluctuation. It's the initial conditions of the problem.
it grows with A. Ah, yes.
No, because
Ah,
now I
yes.
factorized it, right? So this grows with A and this doesn't change.
Right. So,
So-
okay.
Delta tilde is like the growth factorized.
Okay. So it's the initial condition.
Yeah, exactly.
Okay, but this doesn't catch logarithmic growth.
This what, sorry?
Doesn't catch logarithmic growth.
Well, the thing is that in Einstein de Sitter, since it's a scale-free universe, because there's only matter and no other component, I don't think you have any logarithmic growth
No,
anymore.
but you know that matter grows logarithmically.
During radiation domination.
So it's
Yeah. Exactly. Okay, so I'm going to plug that in, right? So I'm going to basically write something that looks like delta 2 prime plus theta 2 equals minus, and then if I just do this delta integral, I can kill one of my k1, k2s, and I can do this here as well. So I get something like q alpha q k minus q theta 1 of q, and then I will get delta 1 of k minus q, right? So now I'm restoring my nonlinearities, but only with the first order solution. I can do the same here as well, so theta 2 prime plus theta 2 plus 3 halves, another matter, h squared, delta 2 equals this, and then I'm going to have beta of q, k minus q, and only theta of q, theta of k minus q. So people are okay with the fact that I now went from k1, k2 to q, k minus q. That's just a delta function integral that enforces momentum conservation. And so I have these equations, and now what I'm going to do is I'm going to try to search for solutions. I'm going to plug in solutions that look like some kernel times q1, some kernel which couples two momenta times delta q1, delta q2, and some momentum coupling. And I'm also going to search for a solution here that looks like G2 of Q1, Q2, and then delta of Q1, Q2, and my Dirac delta. So what I'm trying to do is I'm trying to say, oh, my second order solution has to be 2 powers of the linear solution, but with some mode coupling constraints, some kernel that I have to find. But it should be related to the only other thing that couples modes in my problem, which is alpha and beta. And since the linear solution for velocities is the same as the linear solution for densities, I can always just search for things that are powers of densities. If you do a lot of algebra, and you can look at the notes, so you basically take these, plug this into here. You have to be careful about the time dependence because this is an eta derivative, and A depends on eta, so there's some subtleties. But if you do all of that math, then what you get is basically that F2 of K1, K2 is equal to 5/7 of alpha plus 2/7 beta. And you also get that this G2 of K1, K2 is 3/7 alpha plus 4/7 beta. So the mode coupling for the density fluctuations is mostly driven by the mode coupling in the continuity equation. It's 5/7 versus 2/7. For the evolution of the velocity perturbations, it's actually mostly this, but it's actually pretty comparable. And now we can do this to nth order, right? So what people then do, and what people have done, is people actually write something that looks like delta van, and also the same for theta, but I'm not going to write it down, is some integral over Q1, Qn, with n powers of the linear solution times some Fn kernel times a delta function that conserves momenta. So this is k minus q and sum together. And you can actually write a recursion relation to generate all of these at all orders.
It looks like a looping.
Great. So we now saw that starting from these equations of motion, given the structure of these nonlinearities, we can have basically infinite order solutions. Every order couples n linear modes together in some way, which is prescribed by this coupling kernel. One comment that might be interesting is basically every time you take 2 modes opposite to each other, so the following thing holds true. So basically you take all of your n modes except for the last 2, and then you make them very hard. This always goes as k squared over q squared, where k is the sum of all momenta. So when you're trying to understand the structure of divergences in the theory, this result is very helpful, which we'll sort of do in a second.
I'm sure there's also soft limit.
There's also soft limits. Exactly. So this is very important for these like consistency conditions of large-scale structure, for example, where you take soft limits of correlators, and the soft limit of the 3-point function is some combination of 2-point functions, etc. Okay, so what did we do, right? We took the equations of motion for the dark matter fluid. That was this Vazov equation, assuming it was collisionless and perfect. We took moments of it and converted it into this continuity and Euler equation, which still have nonlinearities. The nonlinearities actually are pretty prescribed. You can understand them well. It's just this sort of theta-theta beta coupling and this theta-delta alpha coupling. So if you want to look at papers about the LSS bootstrap, they sort of investigate this fact a little bit more, that it's a simple coupling. Like you don't get a delta-delta coupling, for example.
So who's working this LSS bootstrap?
There's a paper by Guido and a paper by Marco Marinucci. I really like, and sorry, those two are together, and there's also a paper by Tomohiro Fujita and Zvonimir Vla, which is also quite nice. Right, so at any order we have n mode coupling kernels for f and for g. So we have basically something like n interaction vertices. And this also means that we can write down these solutions in some sort of diagrammatic fashion. And so the basic idea, right, is that whatever this nth order solution is, I can just always write this.
The coupling constant is delta linear.
Hmm?
The coupling constant is like delta linear.
Yes. I mean, I guess it's this f, right? But that depends on momenta.
F is the loop integral, or the. Okay, go ahead.
I mean,
Oh, sorry.
Here in the delta 2, this is f integral f2 delta 1 delta 1.
Yeah, sorry, these are always 1. So I can write this equivalently as my external momentum k with some mode coupling structure, Fn, and all of my legs. So this is going to be something like, for example, Q1, and this is Qn, and every time I have something like this, I'm enforcing momentum conservation. So, you know, delta 2 is going to have 2 legs, delta 3 is going to have 3 legs. So you get something that looks like this, something that looks like this, so on and so forth. And now actually I'm just going to completely ignore any solutions to theta, because that only matters when velocities matter in the problem, but I want to compute the power spectrum of density fluctuations.
These Q's are integrated.
These? Yes.
Yeah, so this external leg moment integrated. So it could
No, because I have this mode
it's
coupling.
one delta.
Yeah.
So
But it couples all the momenta together, so I always have one leg that's...
only one leg is not integrated. Well, that's
but this is the diagrammatics that you use when you're gonna, you only have a loop when you close something, right? Like you only integrate over all these momenta at the end of the day when you close the...
yeah, but you integrated over all Q1, Q2, Qn, so subject to the delta function.
Mm-hmm.
There's just one delta function.
Yeah, but I can't write, yes.
So there are loops there somewhere.
No, this is just how I would write the solution. So this just comes from the Feynman rules. So
yeah, you can interpret as incoming particles because they're
They're integrating over incoming
Yes.
particles at fixed momentum.
no, these are not incoming particles.
They're not incoming particles.
yeah, no, this is I mean, when people try to make this like QFT-esque, a lot of the analogies don't actually work that well.
I like EFT-esque.
Because it's not QFT, right? You don't have a Lagrangian. You're doing this at the level of
But
electricity
you
motion.
might want, you don't have because you didn't write, but it might be possible to derivate the Lagrangian from which those two equations come from. Those two equations, they come from a Lagrangian.
Yeah. No, I mean, people have written Lagrangians for fluid mechanics, but I think they're a little bit... Yeah. I mean, yeah, so Rogério, here, I mean, the point is just, yes, eventually, but I also never write my density field like this. I only write it in this diagrammatic language when I want to couple it to some external leg as well. So really the objects that you have, and I'm going to get into this now, are like the propagator is the fundamental building block, and then you always attach legs through this propagator, which is going to be the power spectrum.
Here you write the diagrams for equation of motion. So the Feynman diagrams are diagrams for Lagrangian interaction. So it's something for interpreting.
Okay, yes. So now that I have my nth order solutions, what can I do with this? I can compute. I can compute summary statistics. I can compute correlation functions. Yeah.
But you haven't told us by how much the n term is smaller than the n minus 1.
That's very true. So, I mean, I can do this calculation for you now. I'm going to compute something instead of...
Isn't it by a factor of delta linear?
Well, yes, but let's think about delta linear. So I said delta was 1, right, in some sense? Or sorry, delta was small, less than 1. So maybe what I can do is I can think of the variance of delta, and that tells me roughly how much randomly I get a patch of the universe that is larger than 1 or less than 1, right? And so if I compute this, it turns out that this is like P of Q. P of Q goes as K cubed. K to the minus 3. So at this point, this will scale as dq q squared q to the minus 3. And so even the linear solution actually technically diverges. So this is why this theory is actually very problematic. Because for precisely the kind of reason that you pointed out, there's no good bookkeeping parameter. It's not delta, because even in linear theory, this is just a linear power spectrum, its variance is infinite. So that's hopefully what I had no idea how I'm doing on time.
No, you have plenty of time.
Okay. Yes, Louis?
People can leave if they are higher.
What is the time actually?
It's 5.
Now it's fine, but it's okay.
Yeah.
Well, but there is something that I don't understand in the process, that is to do the decomposition in terms of scale factor. And then, when you write the first equation for order 2, why are you sure that you don't have?
Sorry, say that again?
Why are you sure that you don't have other stuff?
Other time dependence, you mean? So basically the problem that I'm treating right now is this Einstein de Sitter problem. So it's a universe with omega matter equals 1. So if omega matter equals 1, I have no other component. The only possible time evolution that I can have is the expansion rate of the universe. There's no, for example, epoch where my time evolution switches from something to something else. It's kind of like a de Sitter universe, right? But de Sitter is exponentially expanding. So the only kind of time dependence that I can have is powers of the linear solution of the time dependence. If you treat the problem in full normal lambda CDM, then d of z, you get powers of d of z here, or you get something that's a more complicated function that you actually have to solve for the time evolution. This is just an approximation that I made to a specific kind of universe. It doesn't hold always.
My question is that when you do a project of 2 order 1 stuff, you will get order 2, the scale factor. It's not very clear to me that the expansion that you're doing has to be in the scale factor or not. So
It's not really in the scale factor. It's actually, right, because yes, a2, a squared is smaller than a, but even delta had an infinite variance, and so delta's the second order solution is going to have also an infinite variance. So this is, right now, not actually a very well posed extension, which is part of the problem with the theory and why it took a long time for it to be of use.
yeah, because if you, the thing that I think that you will show that if you get only at order 2, then you have some problems.
Yes.
You have process back.
Yes.
Stuff to control.
Yes, yes.
But is it race correct if you would go to infinite order, right?
No, actually. Even at infinite order. So there's a very nice paper where people show, they study the 1 + 1 dimensional version of this problem. In 1 + 1 dimensions, this Lagrangian frame is exact. It's the exact solution. And you can show that in 1 + 1 dimensions, if you can write the nth order solution, take the limit of it going to infinity, and it does not recover the exact solution. So there's no sense in which this is like it's not convergent, it's not even asymptotic, right? It's just the linear term is already bad, basically. Yeah. So hopefully we will, if I have time, I can fix this. I can try. But yeah. So what I want to do now is I want to compute things. And so I want to compute correlation functions of these fields. And we can just look at the 2-point function right now. And so the 2-point function, right, is going to look something like this, schematically. So if I just plug that in, I'm just going to have a sum of all of my terms with momentum k, all of my terms with momentum k prime. So I'm going to get one term that looks like delta 1, kk prime. This one's okay, this is my linear solution. I'm going to get a term that looks like 2 times, or with a cyclic term, that delta 2, delta 1, kk prime. I'm also going to get a term that looks like delta 2, delta 2. And then I'm also going to get a term that looks like 2, delta 3, delta 1, and so on and so forth. So morally, what do each of these correlation functions look like? Well, if I take my expression for delta 2 over here, it's f2 delta linear. And so always what I will get is something that looks like a sum over terms ij, some integral over my Fi, Fj mode coupling kernels, and then a correlation where every single field is linear and Gaussian. So now I will have delta 1 Q1 until my delta I, and then I will have delta 1 Q prime 1, delta 1 Q prime J. And so this is kind of ugly, right? Because now even the power spectrum, this 2 term over here, is going to have a 4-point function, but every single one of these is Gaussian. So what we can do is apply Wick's theorem. And so what this means is that what we do in large structure perturbation theory is you always reduce your problem to some large endpoint correlation function of Gaussian fields that are linear, and then you compute this with Wick's theorem. And then I guess Wick's theorem, if you are not familiar with it, is the following. It's a theorem in statistics. It's a theorem that you see when you take QFT for the first time, because very similarly, your free fields are normally Gaussian fields. And so when you write things in a perturbative expansion, your correlation function of an interaction is going to have even numbers of Gaussian fields. But it's basically if you have something that looks like delta 1, delta 2, delta 3, delta 4, and all of these are Gaussian, then this actually factorizes into all possible products of 2-point functions that you could write down. So you get something like delta 1, delta 2, delta 3, delta 4. So this is the correlation of this function times the correlation of these two terms. I can do delta 1, delta 3, delta 2, delta 4. And I also have some momentum conservation here always from the power spectrum. 1, 2, 4, plus. Plus my other term here, which is going to be delta 1, delta 4, delta 2, delta 3, delta 1, 4, delta 2, 3. So that's it, right?
So this is always, you have always have even numbers? Because like delta 2, delta 1, you have a 3.
Right, so if we have delta 2, delta 1, then we're going to have a term that looks like this.
This is 0.
But this is 0. If this is 1, 1, 1, because there's no skewness to the Gaussian field. So in this case, what we also see is that we always have the linear power spectrum. And so the linear power spectrum is like the propagator of this perturbation field. So it's the building block, and whenever you want to compute some correlation functions, so now what I do is I have some delta k at some order, and I'm going to have to attach some external legs, connect them through the propagator, and then integrate over everything that's left. So I will have loops, but I will be always integrating over everything that's left. So I guess I don't have anything that looks kind of like a tadpole type term in LSS. So let's compute the first correction to the power spectrum. So the first correction to the power spectrum, so it's delta is the linear solution plus the second order solution. And so if I compute delta delta, this is the 1, 1 contribution that I wrote over there. So this is k prime k, and this dot is p linear. And then I'm also going to connect something that looks like k, an F2, but then I want to connect it with the external term here, which is F2. And so there's two ways that I can connect this basically, right? So I will have either this leg and this leg, or this leg and this leg. And when I connect these linear legs, I get something that looks like this. So this is p linear, this is p linear. And so as far as equations goes, this actually ends up looking like 2 times the integral of d3 cubed over 2 pi cubed, p linear of q, p linear of k minus q, and then 2 powers of F2 k minus q q. And then actually implementing this on a computer and computing it quickly is was a big problem for a long time, recently solved. FFT log is very important in all of this. But this is what the 2-2 contribution looks like.
And the integrals converge.
Hmm?
And the integrals converge.
No.
So I cannot put this in a computer.
Yeah, so this is what we call P22. The other contribution that you can do, so this has...
P12 is 0?
P12 is 0, right? And so the next contribution, so this has 2 powers of the density field. This has 2 powers of the density field. So could I just keep, this has 4 powers of the density field. So I'm missing one more term that has 4 powers of the density field, which is the 3 and 1 contribution. And so if I do the 3 and 1 contribution, the diagram for that looks like something like this with an F3, and then I just want to couple this to some external leg, so I can always, pick one and then close the other loop. And so this is equal to something that looks like a propagator, a modified propagator term. So this is F3. There's a P linear here.
That's a tadpole.
I mean,
That's what we call that.
that's what you call. I thought that a tadpole was something like this, with like no. Yeah, we call these propagator terms because I guess this. I mean, which is weird, right? Because when we think of like vacuum polarization, this is the diagram, but this is what we call. Because basically the reason is that this is just 3 P linear of k, right? We have an external leg here that we had to close with this one, so this is just a linear term. And then we have integral of d3q over 2 pi cubed.
So technically it's not a tadpole because he received contribution of momentum of volume momentum equal to 0.
And then f3 with k, these two terms folded back into each other, an integral over all p of k, and then an original linear power spectrum. So this, in some sense, just modifies the linear solution. It's some scale-dependent modification.
There should be the linear power k should be to the 4 at the end.
No, so the power spectrum is delta squared order,
It's delta 4, so it's p squared.
and so it's p squared, p squared, p squared.
Sorry,
Yeah.
This is a P31.
Hmm?
This is P31.
Yes. So this is what we would call P13. This language is actually really nice because now if you want to compute higher order correlation functions like the bispectrum, which people care about a lot, at linear order this is 0, but then it actually turns out that it's the third order solution is just something like delta 2, delta 1, delta 1. So I just write this diagram over here. I have a leg here, I have a leg here. I just have a linear power spectrum here and a linear power spectrum here. And so, oops. So this is just, for example, like 2 F2 of K2, K3, P of K2, K3, plus all of my cyclic permutations from which field I take to be second order, so on and so forth. So this is nice. This gives us an order by order scheme to calculate corrections to any summary statistic in large scale structure because of nonlinear growth. But, as we kind of mentioned, even the linear theory solution diverges in some sense, so, okay. I was going to discuss some of the divergences, but I don't know for time, maybe because I wanted to get to the EFT part.
This is the old approach, Stochimara approach.
Yes, exactly.
So I quite got to the...
No, but you can't get to the EFT without discussing this at least, so...
But then
Yeah.
do it.
Still something that I don't get.
Mm-hmm.
Expansion that you do delta 1 delta 2
Mm-hmm.
it's not an expansion like in terms of Taylor expansion.
No, it's some...
This is the term that varies at the percent of a to the 1. This is the one that varies at a to the 2.
Mm-hmm.
And how do you assume that everyone is smaller than delta 1?
Well, because you thought delta was less than 1 in some sense, and so of course the term that's delta 1 is smaller than delta. But like I said, this is a problem. You haven't formalized any sort of scale for how you do this. So I wanted to show a figure very quickly of what these solutions look like. So what I'm showing is basically if you coded up those equations and put them on the computer, the black line here is the linear theory solution. The blue line is the 2-2 solution. The green line is the 1-3 solution, which is always negative. And actually what's really interesting, right, at small scales, individually the 2-2 and the 1-3 are like orders of magnitude. This is a log-log plot, higher. So it's not a perturbative solution at all. However, each of these terms are very high because they hit the UV divergences of the problem. It doesn't actually quite diverge. And actually this divergence cancels almost exactly, right? So if you subtract the two terms from each other, you get if you sum them, you get this purple line. And so then what you're really doing is you're summing the black curve in this solution. So this is what these sorts of corrections look like. But even then, of course, at this scale, over here at k of 0.2, what you thought was your perturbative correction is the same size as your linear theory solution. And so there's no guarantee that your next order correction isn't going to be even larger. You don't have any control over the theory right now. But this is what this looks like. And I guess since I'm already on Tobias's notes, I can scroll down a little bit and just point out, if you assume that the universes are power laws, each of these terms individually has UV divergences that cancel, and also IR divergences. The IR divergences also cancel amongst themselves. The full spectrum is actually still IR divergent, but only for really aggressive power law spectra. I guess one other comment that I thought was interesting is that people have understood that this IR divergence in each individual term canceling is a result of the like Galilean invariance. So if you go to GR corrections, which is stuff like Jorge Noreña, who's come to lecture here many times, works on, then actually Jorge Noreña, he's a professor at PUC Valparaíso, then you don't have Galilean invariance because you're in GR, and then the IR divergence doesn't cancel exactly, and so you're much more sensitive to IR modes, which is kind of interesting.
So this is beyond GR?
If you go to GR corrections, so horizon scale corrections, which are IR corrections.
Okay.
Yeah.
So it's within GR, but take into account.
Exactly. Within GR, but take into account horizon scale
But
effects.
all of this was Newtonian physics in expanded universe.
Exactly. Exactly. Okay, let me turn this off. So anyway, the point is, you can, if you look at these notes, you can look at the structure of these divergences. And we're just kind of lucky, actually, that when we put this integral on the computer, for lambda CDM specifically, it doesn't diverge. Just luck, basically. Basically because of the power law slopes being k and k minus 3, if this were slightly different, it would actually formally diverge. Instead, we just get very large contributions from arbitrarily small scales. So, as all of you have been pointing out repeatedly, there are a lot of problems with this construction. And that's why it was very difficult to implement it as far as data analysis goes for a very long time. So, like I had sort of mentioned, right, the linear variance diverges. And so, is there some way that we can rewrite this theory and try to have a little bit more control over the scales in the problem that are linear and the scales in the problem that are nonlinear? So let's go back and let's compute this variance of the density field in real space, which is just this integral, or which is just this expectation value, which looks like this. And so if I do the angular integral, I get something that looks like 1 over, actually, look this. So it looks like k d log k cubed p of k over 2 pi squared.
That's linear, P of k?
Linear, yes. So this quantity here is dimensionless because p of k has units of volume, k cubed has units of 1 over volume. So this is a very interesting bookkeeping parameter because it tells us what the dimensionless contribution to the variance of the density field is, and in sort of a decade by decade sense. Each k mode, what is the dimensionless contribution to the variance? So as soon as this equation gets, as soon as we find a k where this k cubed p of k over 2 pi squared is order 1, then this means that scales larger than that are contributing order 1 or more to the variance of my fluctuations. So this lets us look, we can define the nonlinear scale in the problem, delta k and l, to be when this function crosses 1. So specifically this is a k such that if you multiply this function by k cubed, when it crosses 1, so it kind of flattens out, it actually grows logarithmically at high k, because this is actually log squared of k. When this function crosses 1, all scales after that are always order 1 in terms of variance of their fluctuations. They contribute nonlinearly, we don't want them. So let's try to formulate a theory with some cutoff lambda, which is always less than this k nonlinear in my problem. And then if I integrate out all of the contributions higher than this lambda, the theory is actually well posed. So this is fundamentally what this EFT program was trying to solve. And the sort of physical intuition for why you might imagine this happening is, for example, if you've ever looked at an n-body simulation of structure formation, you start from this actually homogeneous fluid, you start to form these structures, these filaments, these sheets, halos, and these halos are sort of a collection of particles that are orbiting each other after virialization, which is a nonlinear, non-perturbative process. A halo has a velocity dispersion, right? If you just were to compute all of the particles associated with that halo, they very clearly have a velocity dispersion. They're sort of supported, there's some pressure in some sense. So very clearly, at some point, at certain small enough scales, when these effects start to matter, I can't actually say that there's a zero stress tensor in my problem. My building blocks of large-scale structure, these halos, have a non-zero stress tensor. And so kind of the goal of the picture was to figure out how does a stress tensor show up here. A stress tensor is also interesting because it's dissipative, and so this also introduces dissipative dynamics into the problem, which means that you have some way to make smaller scales, higher energies matter less and less because of dissipative processes. So I think that's all that I wanted to say. Oh, shit, hold on. Oh, okay. So I now wanted to comment a little bit on this EFT approach, right? Finally. But the truth is that the EFT approach, the reason you have to do all this is because it makes no sense to motivate this without an understanding of why you have built that, right? So there's two formulations. One is we're going to explicitly introduce the scale into the problem lambda. We're going to coarse grain the equations of motion. We're going to apply some filter and study the filtered equations of motion. So this is some explicit coarse graining procedure. The other thing that we can do is actually just sort of do some, I don't know if I would call this Wilsonian, I guess, but you can do a sort of top-down approach. Instead of trying to build up what the structure of the divergences is you stare at this guy, and you stare at how does it diverge, how does it not diverge in the UV and in the IR, and you just rewrite the theory to have counterterms that absorb these divergences, and you do the same for P13, and you go to two loops, and you do the same for the two loop contributions, and so on and so forth. I guess maybe it would have been nice to mention, so P22 has a divergence that goes as k to the fourth. So if you expand this kernel properly, you get something that looks like k to the fourth times some finite term.
You said if P goes like 1 over k cubed, there's no divergence.
So if P goes as 1 over k cubed, no, so I have to remember the table exactly. So the integral is finite, but it still gets arbitrarily large contributions, right, from small scales.
It's finite, but then larger.
But really large, exactly. There's no decoupling of scales in the problem. So, yeah. Well, it's okay. I can get to that when we get to that. And so the other approach is to just study. You study the UV structure of correlators. And then you renormalize the correlation functions to have no UV divergences. So this is kind of, you know, how I guess you can write down new terms in a Lagrangian when you write some Yukawa interaction, for example, see that you get some loop. This loop renormalizes unless you have a counter term that actually looks like some phi to the fourth type thing in scalar Yukawa. To me, that's the analogy of how we think about this. And so I'm going to give this construction here because I think it's physically a little bit more intuitive. And so what we're going to do is we're going to go back to those equations of motion, the continuity equation, and the Euler equation. And what we're going to do is we're going to apply some filter with some scale lambda. The precise form doesn't matter. It can be a top hat filter in Fourier space. It can be some sort of Gaussian filter. It doesn't change much. But what we're going to do is we're going to apply some filter, and so we're going to define what I call large scale operators. So these have some subscript L for long or large scale. And these I always define as this convolution between my filter and my original quantity. And so generically, you basically can always write for some function x of L, you define it as this filtered version of this x. So this is and also kind of trivially, what you see is that you just say that the full thing is the sum of my long plus my short. And so you always have the large scale contributions. This integral has some cutoff. What I'm going to call the short scale contribution is all of the modes that are beyond that cutoff. That would, and the sum of them together gives my original operator that I have. So now what you do is you basically take this filter and you multiply it against, so this is a lot of algebra, so, oh yeah.
But the small scale contribution like this is also filtered.
No, so the idea basically, so if this is some k mode cutoff, for example, right? So this is like from 0 to lambda, plus from lambda to infinity. So this would be my x long, and this would be my x short.
Right.
Yeah.
Right. In that space, x short would be the convolution with the delta minus w.
With the...
I mean, if
yes,
x long is the convolution with w, x short would be the convolution with delta minus w.
Yes.
By definition.
Okay. So then what you do is you basically take this filter and you do something which pictorially looks like this. And you do the same thing with Euler. So you just take this filter and you apply it to both sides of the equation. And what you get is the following. And then you reorganize everything in terms of long and short. And it actually turns out that for the continuity equation, nothing changes. So the continuity equation in terms of all of the filtering after you've done it just looks like delta long prime plus dj 1 plus delta long v long j equals 0, which is a little bit surprising at first glance because this is a nonlinearity, but it turns out that the right way to build this smoothing for the velocity is at the level of the momentum, which is the product of these two things. So everything actually ends up factorizing. And I can give you a reference if you want, but this is the construction from Boltzmann, so this is what you get. And then kind of more interestingly is that if you do the same thing for VL prime for Euler, you get a term now. It's not 0. You actually find some effective stress tensor shows up when you do this operation. And the reason why you get something that shows up is because if you think of the original Euler equation, this rho is actually on the left-hand side, if I were to write this with some stress tensor. When I do all of the smoothing, because I don't want to do the smoothing with something in the denominator, I get a product of V times L, I get a product of, rho times V, I get a product of rho times nabla rho, or sorry, nabla phi. If you treat all these contributions carefully, this is in the appendix of this Baumann paper, you get something like this. And what you also find is that this term here is written, and I did not write it down exactly, but this actually looks like only short modes. So this looks like something that looks like V short I, V short J, and you also get a contribution that looks like dk phi short, delta ij, and a term that looks like minus di phi short, dj phi short, and some combination. So this tensor is actually only written in terms of the short mode fluctuations, and so now I have something interesting. My equation for my large scale modes, and these are well controlled, right, because they're always valid in a regime where the variance is smaller than 1, I have generated something that looks like a stress tensor from the short scale modes, and this stress tensor will introduce dissipative dynamics.
This is not the sigma of earlier.
This is not the sigma of earlier. Even with a 0 sigma, you would get something like this. And that's kind of the trick of the EFT. So it introduces this dissipative structure back into the problem, even if you neglected it at the start.
So what does it mean, the square bracket lambda? It means that you're...
It means that you filtered it on some scale lambda.
But these are only small scales, so the filtering, does it matter?
I mean, the sum of two small frequencies can give the sum of two high frequencies can give a small frequency, because if they are almost equal, their difference is a lot.
If you have a convolution of two functions that only have support at high frequencies, this gives you support at low frequencies again. Yes. Sorry. Sorry, Louis, I didn't mean to attack you.
If you have a small frequency and a high frequency, you always get a high frequency.
So there's a lot of subtlety now for how we treat this. Oh, thank you. Fundamentally, what people end up doing is basically writing down an ansatz, where you take this tensor, which is defined only in terms of small-scale modes, and you re-expand it in terms of how these small-scale products depend on large-scale quantities, plus a term that is called stochastic, which is truly decorrelated from everything else. So fundamentally, what people end up writing, and you can either look at Tobias's notes or the paper, they do this very carefully, but it's just quite long, is you actually end up writing this as some sort of pressure component plus some term that looks like a sound speed for my fluid, where now I get a dependence explicitly on the long density. So when you do this re-expansion carefully, you get something that depends on the large-scale density again.
Is that a tensor, or you can actually do that?
They actually showed that you can write it in this way, but this is also the sort of standard stress tensor fluid that you would write down in fluid mechanics. So this is the standard ansatz that you would do for that. But they show that you can actually map this from one to the other.
A little bit of intuition how short modes combine to make a long mode?
Well, this is, I guess, what we were saying, where if you have some sort of integral over all frequencies, and you have something that, Q, and you have like Q and K minus Q for your arguments, right? Then for small k here, you can basically, even if k is small, right? You have Q which has support and Q which has support, and so you get something that looks like low k at the end of the day.
I mean, when you take the product of two oscillating signals, the result has both the sum and the difference. So the difference can be small, and so it can be long wavelength. The sum is always right, but the difference can be small.
Something called Wicking.
Yes,
So then you also get terms that look like velocities. So this was a sound speed of my fluid. You get something that looks like a bulk viscosity of the fluid, because it's just a divergence of the long velocity mode. And then you get another contribution, which is called the shear viscosity, because this looks like sort of the shearing, the quadrupole contribution. Plus a term that is uncorrelated with the large scale quantities, right? So this is large scale, 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 and then truly whatever's left, I have no choice but to call it stochastic. And I don't know what it looks like a priori. So what I'm calling these terms, so I'm expanding this into basically two sets of contributions. Contributions which are correlated with the long modes. So this is the part of the beat coupling that gives me something that's large scale, and a part of the beat coupling which is really only small scale, which is the stochastic contribution. So I can always correlate delta with delta, velocity with delta, long. If I try to take any correlator in my perturbation, in my EFT, with this remaining, with the trace of this, with the divergence of this operator, I will get 0. Yes, because it's sourced by modes that are so small, I can't treat them, I might as well call them random. They're decorrelated for my problem.
So this is the most general expansion of an energy momentum tensor?
That is linear in the long modes.
That is a linear.
So I have I'm expanding in things that are a vector, a linear and a vector, and a density. So I can only take, and I have to write a tensor, so I can only do a scalar part for this decomposition. I can do a trace part for my vector, or a trace part for this matrix built from the vector, and then the quadrupole part, which is the traces contribution, and it's symmetric.
Right.
So if you have anisotropic stress, then you would have something that makes this. Actually, no, that would be the shearing viscosity.
And those parameters, CS squared, the velocity, viscosity, the velocity, the shear velocity, those are free parameters?
So those are all free parameters that depend on the UV theory. So these are the Wilson coefficients of the theory at the end of the day. And in principle, you can either try to measure them in simulations, which is a UV complete theory, or you can try to fit to data simultaneously and infer what they are.
So if you go to higher orders, you get more coefficients.
Yes. I think it's, so there's 3 right now at linear order, but I would like to invite you to consider the following. This is not the contribution that actually matters into the equations of motion. Remember that I scalarized the Euler equation, and this already had like a dI/Tij contribution. So actually, what I want to really do is take what I'm going to call, well, you take dI, dj, this Tij lambda, and what ends up happening at the end of the day is that this contributes with, at linear order, just one parameter. So this actually looks like rho bar CS squared d2 delta L. So this is a higher derivative correction now. Minus some effective viscosity d2 theta L plus what I'm just going to call the stochastic term, which we call J. And at linear order, remember delta and theta are equivalent up to some dimensionful scaling. So really this is just one free coefficient that actually impacts just d2 delta L. So basically, this object acts as a source for the equations of motion for Euler. So I can solve them now where I knew the solution to the homogeneous part plus this source. You can write a Green's function for it. But fundamentally, the only thing that changes is you're adding a solution to this unhomogeneous part, which looks like d2 delta, which in Fourier space looks like k squared delta.
So that changes what you call G, the G function, G kernel?
Yes.
Because the G kernel is for the Euler.
Yeah. Well, no, so it doesn't change that. It changes the Green's function that you write down. The kernels themselves are still the same because they're the solutions to the homogeneous part. of the equation, so you only have to find a solution to this, which is just adding something like this to your density field, it turns out. So now, this is the EFT one loop density. It's actually delta of k and eta, is delta 1 of k and eta plus delta 2 plus delta 3. So there were no parameters here.
K squared delta linear.
Minus k squared cs squared delta linear of k eta plus the stochastic term. And so the idea, right, is that you can now take correlations and you will have a new solution, which is that the P EFT is your P linear plus your P22, which now depends on the cutoff explicitly from the regularization, plus 2P13, which also depends on your cutoff, minus the contraction that I can write down between this guy and this guy. So this is 2 cs squared k squared P linear, plus this doesn't correlate with anything, but it does correlate with itself. So we write this as a stochastic spectrum.
So, these are deltas that are the same delta as before.
Yes, but I now have an explicit cutoff in the theory. So the loop integrals don't run over all momenta, they only run up to my lambda.
And I missed it, but how did you introduce k squared cs squared and the delta?
So the idea is fundamentally when I have this in my Euler equation, and I show that it looks like this, then this only looks like d2 delta L and d2 theta L. These are the same. And when I go to Fourier space, this d2 becomes a k squared. And just adding something like this to your solution captures this inhomogeneity.
So this is the theta transforms into this system.
Yes, because at linear order, theta and delta are the same.
And there's the tau aj
The tau aj, yes.
transforms into something like this.
So the equation that solves the Euler, the variable that's the density field that solves the Euler equation in the presence of this tau, when I expand it like this, is actually a term that looks like k squared with some free coefficient, cs squared delta, linear. And this is linear in delta, so it kind of makes sense. Okay? So we have this. This is our one loop solution. This actually scales as k to the fourth. So it only really matters at super high momenta where we wouldn't trust this theory anyway. It actually turns out that the divergence in P22, so this has a UV divergence, which also goes as k to the fourth. And so what you can then do is just redefine these things to have this divergence go away, basically.
I'm sorry to ask.
Mm-hmm.
Is there any way to understand why you have a minus, why you have suppression of the power spectrum due to this effective term?
Well, if you think of it as like a dissipative term, then as my scales go higher and higher, I shouldn't be as nonlinear as I thought I was going to be.
So it's like a dissipative.
Yes. So now let's look at this P13 term in the presence of a cutoff. So this is P linear, integral from 0 to lambda of d3q over 2 pi cubed, f3 of k minus qq, P linear of q, plus the same contribution from lambda to infinity.
Can I just
Yes.
interrupt you? Even you're saying loop level, but even at tree level, you have this effect of this dissipative term in Princeton.
Mm-hmm.
Even at tree level, we can even forget the P2, P3, etc.
Mm-hmm.
Is that correct? That's correct.
Yes, but so if you write this in a scaling universe, then you basically see the sizes of these contributions as k over KNL to some power. And then basically what you get is that this looks like k over KNL to whatever n you had plus 2.
Well, KNL does not appear.
Well, CS squared is dimensionful, so this should be order 1, right? So this should be some order 1 dimensionless coefficient divided by KNL squared, or divided by lambda squared, in some EFT sense, right? No, it's some effective sound speed. It's not a real sound speed now. So you can even have cases where the CS squared is actually negative. But no, it's just something about the effective. It's just some parameter, basically. So if I now look at the structure of this theory, right, with the cutoff, I have my finite part, and now I have my UV part. And it turns out that if you expand this term in the argument of k being much smaller than q, which makes sense, right? So I have p linear of q, and then I have this kernel. And that's exactly that limit that I had written down, which is the k squared over q squared, the hard limit. Then what I find is that this looks like p13 lambda minus k squared p of k times 61 over 2/10 of 1 over 2 pi squared, 1 over 6 pi squared, the integral from lambda to infinity of dq times p linear of q. And so what I can do is just redefine this coefficient, which should also depend on lambda, to be this coefficient plus this term over here, which is just a k squared times this. And what this does is that this renders my theory insensitive, right? So my final prediction doesn't depend on lambda, because my P13, basically the divergent part, I've reabsorbed it into whatever this coefficient was. So this coefficient will change as I change lambda, but always to cancel whatever the dependence was here. And so this way you can render the theory to be, the prediction is independent of the running. And then you have one free parameter at the end of the day. Yes, Lou?
When you compute EFT, you don't have a term that is delta 3 times k squared CS squared delta 1.
Sorry, could you say that again?
When you compute EFT, you don't have a term that is delta 3 times k squared CS squared delta 1.
You do, but if you do the power counting now in terms of k squared over lambda squared in this finite universe, that would enter at a much higher contribution. It would basically only be relevant at even smaller scales. So something like that looks like it's a two-loop contribution, basically. But you would have it in principle. But you can see even here, right, with the scaling. So this high k contribution also goes as k squared, so you get something that goes as k to the fourth. So if k is smaller than lambda, then this k to the fourth over lambda is always going to be a subleading contribution. Okay. So now I can redefine things. And so I can define CS squared infinity, which was my original CS squared, minus 61 over 2/10, 1 over 6 pi squared. And this is now my free parameter. This is my renormalized parameter that I try to fit to data. Instead of writing the bare theory, I wrote it in such a way that my prediction is stable. And that's the EFT of LSS, basically. This is the first correction that you get. If you try to build the bispectrum at one loop, then you get, you need to expand the stress tensor to higher orders. If you do the power spectrum at 2 loops, you get new parameters that show up, not just this one. At 3 loops, even more. At 3 loops, actually, you are already sort of past the asymptotic regime of the theory, so even though you have more free parameters, you don't actually improve the fits compared to the n-body simulation, which is the UV complete theory at all. So the theory saturates somewhat quickly. I guess I also never mentioned it, right, but this KNL, this nonlinear scale, is always something at redshift 0, something like 0.3. h over megaparsecs, maybe a little bit more. And so you can never really hope to do much better than this using EFT of LSS. So,
This is a lambda.
hmm?
This is a lambda that you get.
Yes, roughly, for lambda CDM. I mean, it depends on all the parameters and the redshift, but this is sort of the order that you should think about. So when people try to fit redshift 0 on n-body simulations, you can't really go much past this.
Did you say, I'm correct, that it doesn't depend on the actual filter that you choose?
It doesn't depend on the what, sorry?
On the actual W, the filter that you...
At the end of the day, it doesn't. I mean, the value of the parameter does matter. The CS will change depending on the filter that you choose. But if you sort of do everything correctly, the theory, the end result should stay the same.
So where does K now appear in this expansion?
So the idea is that you always have some cutoff lambda, which is less than K and L.
So lambda and K and L are related.
Yes.
And K and L you estimate from the condition of the variance. And the variance
Yes.
being 1.
Yes. Exactly. So what did we end up doing, right? Just to sort of recap and start to and wrap up. So we started with this perturbation theory, which was really at the level of the fluid equations of motion, which is, I think, not how we traditionally do perturbation theories, but we did that. For this self-gravitating, perfect pressureless dark matter fluid. And we kind of just computed the one-loop correction after some effort, which involves this 2-2 term and this 1-3 term. Each of these have UV divergences, it turns out, and they're just sensitive to arbitrarily small-scale modes, where we know that this perturbation theory stops breaking down, because the variance of fluctuations on those scales is sort of order 1. And so we need to really reformulate the equations of motion in some way to try to separate scales that are smaller than these scales and scales that are larger, and find how to regulate, basically, what are the dissipative dynamics that regulate the size of these small-scale contributions in some way that cancels exactly the divergence of the theory that we had before. So when you do all of this and you sort of study it carefully, and this is 10 years plus of papers, hundreds of papers on the topic, you get this theory that we understand quite well. So the other approach, right, that what you could have done is instead of going through all this stress tensor blah blah blah, you just wrote this thing down, you did this decomposition, and you said, hey, wait a minute, this diverges as this k squared p of k piece times a part that's finite. And so all that I need to do is introduce a new term in my theory that goes as k squared delta, because that will cut off this divergence, and you would get the same end result. So that's kind of the more modern way that people think about this.
Yeah, but then you have to fix the finite piece of the subtraction by observation.
Well, you can't predict what this coefficient, so this is very different from like a QFT where you have a UV complete theory and you can compute the coefficients from the UV complete theory. Since it's a very nonlinear theory, it's this, n-body simulation, you always have to fit to a simulation's data, or self-fit to the data itself. People have tried to do things, for example, like in spherical collapse, take a spherical collapse problem, smooth over it, and try to predict what the value of the coefficient is. And in spherical collapse, it's 0, actually.
It's what?
0. The sound speed turns out to be 0. There's some symmetry that doesn't let you actually generate something in that problem, which is kind of interesting.
Or you can go to the ellipsoidal block.
Maybe then you could generate something.
Yeah, but then it starts depending on the details. So.
Yes. So the modern approach is really to just try to write the theory in a way that the predictions are finite and don't depend on the cutoff that you write down. So your coefficients will, and then you just fit your coefficients to the data. And so people have done lots of studies, sort of how did these coefficients run as I change the k max in my fits compared to k and l, so on and so forth. People have done studies in scaling universes where you only have k and l as the only scale, like power law universes, and try to extract information from that. It's sort of a really rich field. So where do we go from here? Well, I only told you about the dark matter fluid, right? So what you could do is you could try to figure out how to go from the dark matter fluid to the galaxy density distribution. And this would be biasing theory. And biasing theory also gives you a very similar EFT structure, but with a different cutoff scale. So it's no longer k nonlinear. You get something that is like the sizes of your halos in the Lagrangian patch to the -1. There's a very nice review by Vincent de Jacques, Donghui Zhang, and Fabian Schmidt about this. Not only that, but you also have to go to actually not just delta matter of x, but delta matter of s, which is x plus your line of sight velocity contribution. And so this is redshift space distortions theory. And now you have to write down the perturbation theory not just for delta, but also for the velocities and see how the velocity solutions will change. You also have a different scale here, which is what people call the scale for the fingers of God, which are the scales where the velocities aren't driven by the large scale motions, but only by virialized internal dynamics. You can also do things like study what happens if I take this prediction over here and I try to compute the correlation function. So if I go to configuration space, you will discover that the BAO of the theory is completely wrong because you sort of at some point did an explicit expansion in a parameter that was large, which is this displacement. So there's this whole topic of IR resummation, which you have to develop to be able to treat the BAO properly, which is also where the Lagrangian approach is the most powerful because you get that for free by treating things in the Lagrangian approach. You can always go to FNL and try to figure out how this theory changes with FNL, which is something that people have done before, or the forms of primordial non-Gaussianity. You can try for new dark matter physics and see if this changes the structure of your post-recombination theory. So if you just have dark matter that only matters for the CMB, then you can just use the same exact theory, and post-recombination, nothing changes. But if you have something that is doing funky physics after redshift 1100, you need to see if your equations of motion change and see, for example, if when you have a new Euler equation with the drag term, what does that do to the structure of your counter terms in your perturbation theory? You can always go beyond the power spectrum, which is what I did here. That's also something people have studied very in depth. And finally, you know, even just implementing this P13, P22, the two-loop calculations numerically is a really big challenge. So there's an entire community dedicated to figuring out very fast ways to calculate these things. That said, this is a really mature field. Exactly. So this is a really mature field, so we have various different codes that have all of this implemented. People use it to analyze data every day. It really pushed the boundaries of what people could do with legacy data sets. So with Sloan Digital Sky Survey BOSS, we went from K of 0.1 to 0.2, 0.23. This is a lot more information. So it's been a very fruitful field, but it's very rich, and this is really just the beginning. But also I've been like yelling at you for 2 hours, so maybe this is a good time to stop.
Yeah, what could be taken out of it has already been taken. I mean, there's no hanging fruit anymore.
No, it's definitely. I mean, I think there's fruit in not in developing the theory, but trying to find applications that aren't the standard ones, where these effects could be large, for example. But it's definitely really, really, really mature at this point. So any new developments, I mean, it does seem very difficult from my perspective. And that's also why people like, you know, even Leonardo and Matthias and so on and so forth have started to lose interest in this, because you've really pushed the point of diminishing returns. Sorry?
What is the hope to use this with the Euclid and SST?
I mean, I think Euclid, definitely there's Guido D'Amico's group with this PyBird code, and I think that's going to be one of the fiducial codes to analyze Euclid redshift space distortion data. In LSST, a lot of these perturbative bias expansions, for example, have become really important and are going to be the baseline for a lot of their clustering analyses as well. DES uses this sort of stuff. So it's become industry standard at this point.
It's what goes under the name of fluctuation composites. They don't look only at the BAO, but they look at the whole thing, and then also use this.
You cannot use any linear stuff.
No. So the idea is before you would do a template decomposition where there were only a few parameters that you could measure, but now you actually try to predict in a model-independent way. But now you actually try to predict the full structure of the power spectrum.
And you know, all your logical calibration may have little h, no, because you measure redshift. But you know, when they will have galaxy correlation function in different space.
From LIGO.
No, from that generation.
From what, sorry?
LIGO cannot go that far.
Oh, sorry, but I meant from gravitational waves.
Yeah, from third
Yes.
generation. So in that case, one can. So once you have another probe, the probe that actually